All right, you guys know it's week 11, right? That means we have 3 weeks in November, and we have 1 week in December, and then it's finals week. Yeah, it's rapidly coming to a close, and we've got some stuff to cover. All right, so we've done so far, we've done kinematics. Looks like this pen is not going to make it through class today, but that's fun. We've done kinematics, and this was what we also call translational motion. Okay, so we've done kinematics and translational motion. We've done F is equal to ma. And the other Newton's laws. We've done energy. We've done momentum. Yep, this pin's about to die. So we'll give it up. Well, what we're fixing to do, because I'm always fixing to do stuff, is we're going to do the same kinds of things, but we're going to change the motion. Okay? We're going to change the motion. So translational motion is when I have a block and it's moving either in the X direction or it's moving in the Y direction, or we've got some sort of motion like that. But one of the things is that that's not the only motion that we have, right? Because if I drop a block, my block can also do this. My block can tumble and spin, right? We don't just have a block that moves just in its X and Y direction. When we do, we always love our inclined planes, right? Always love our inclined planes. So on an inclined plane, my block tends to, and we've done it that way, we've tended to have our block just move and slide down the plane. But what happens when we have a ball, a can, a cylinder, a hoop? Not only do we have motion going this way, but my object can be rolling. So we can start getting things rolling, and we can have both rolling motion and translational motion. So we have two types of motion, and one's called translational, and one's called rotational. And in that rotational motion, things start getting a little more complicated. But we can do the same types of things that we were doing before, just that our type of motion is a little different. And we've done this before, we've seen it. I have a tire, right? And if I'm watching this position on my tire as it rotates, it's going to go around in a circle, but I can also have this moving in that direction. And if I'm undoing strings, so let's say I have a string on a thimble and I pull the string out, the thimble or the spool might stay in that spot, but we also have something that's moving in that direction. So we get translational and rotational motion. So we're going to see the same kinds of things that we saw before. And most of you got pinged like crazy. I think it was Monday. Did I do it on Monday? And the blackboard got pinged all over the place because I put in some other videos. I put in links to theorganictutor.com. I put in links to Crash Course from PBS. I put in a lot of different things because when we start thinking rotational motion, even though this is really, really good for us, and there's a lot of examples about rotational motion, and there's lots of things that we can approximate as rotational motion and start looking at it, we don't normally think this way. This isn't the way we normally think about how things move, and we don't normally think about what's happening when we have rotational motion versus translational motion. Yet, Mother Nature really likes rotational motion. Think about it. We spin, the Earth itself spins around an axis. That's why we have days and nights. The moon circles around us, we orbit around the sun, and we have a variety of different things that are there. Which gets me to, has everybody seen on Facebook, there's apparently a big, huge debate about the North Pole. Apparently, what really started the debate, which was actually kind of amusing, was that some Inuit elders had said that the North Pole had shifted. And there were a lot of people that said, well, how would they know? And I'm thinking, well, first of all, if you're living in that environment and you know something's changed, you kind of have a better idea about that. And the problem that most of us have is we're so disconnected with the actual natural world that we don't think about those people who are connected to the natural world. And it's those of us who live on farms know that we get with the rhythms of the animals and the rhythms of the seasons, and you notice them a lot before somebody else does, because we do. Well, it turns out that there was a big debate. Well, they weren't going to admit it unless NASA admitted it. Guess what? The North Pole shifted. At least the magnetic North Pole has shifted. And the Earth wobbles. We really don't spin really nicely. We actually wobble. We precess, very much like a top. So what we're getting ready to look at is some of those motions associated with the top. And that's what we're getting. So the Earth is a big top, and we do wobble. And yes, the magnetic north has moved. It has actually changed. So if you've been following that debate on Facebook, it's most entertaining. But we do spin and we go around, and magnetic north is different. And the other part of it is, this is one of those questions. For those of you who've known me for a while, and Horton Hears a Who is a very disturbing story to me. It's an incredibly disturbing story. It's got the same principle as the galaxy on the cat's collar for Men in Black, or the subway locker in Men in Black 2. What universe are we actually in? That's kind of an interesting, deep concept. So we talked about the North Pole, but is it really north, or are we upside down? So just some things to think about, our orientation out there and how we orient things and how we think about orientation. It gives us a little difficulties in what we do. Is it really the North Pole or the South Pole or whatever? Or could we be this way instead of this way? Okay? Just some thoughts. Just kind of get you pondering.
Taking pictures.
Huh?
Haven't they taken pictures of our Earth from outer space?
Yeah, but the thing is that they may be upside down too.
Yeah.
Think about it. If you're standing on your head, it's upside down. And you all know that your eyeball actually sees everybody upside down, and our brain refers to it right side up. So there's a lot of orientations that give us a little pause, just a little pause. So far, we've been dealing with the world with a lovely Cartesian coordinate system, right? Now we've talked about the other coordinate system, and we've looked at it. So this is one of the reasons that way back at the beginning of the semester, we harped and harped and harped about vectors, right? We've harped and harped about vectors. So we can do the mathematics over here that I've got my vector, and we can actually use the mathematical terms that this x is going to be, if we call this r, that x is r cosine of my angle. And we can call this the projection of that vector on the x-axis. And we've also done this one, and we call this one y, and y sine of the angle is the projection of that vector onto the y-axis. And we could go back and forth between x and y by using the r sine theta. And if we remembered right, we actually said, wait a second, we could use this as something we call polar coordinates. Those are my polar coordinates, and we can go back and forth. And if you want to go back and forth, remember this is like section 1.7 in the book. So you can go back and forth in that exchange between my polar coordinates and my x coordinates, and we're looking at how those things work. But let's kind of look at this for a little bit, because I want to kind of introduce a couple of different things. So if I've got my x and y coordinate system, and I'm going to use a different color. And I have a lovely circle. We can actually call this a unit circle, okay? Where this is my radius of my circle. But if I'm traveling along this circle and I'm moving along the circle here and I'm following a spot on the circle, I want you to look at what happens on the x-axis as I'm moving around the circle. That projection on the x-axis, as I go around the circle, if I start here, as I move around the circle, my x is going this way, and as I come back around the circle, my x is going back that way. So I can move back and forth along the x-axis. Similarly, we could do the exact same thing, and we move along the y-axis in the same manner. We're moving back and forth. That's going to be really important when we start at the beginning of Physics 2, because I usually bring it up in Physics 2. As I'm going around this motion, think about if I have a marker and I'm following it, I actually can represent the motion of my object by a curve that looks like that, which could be sine or cosine depending on which way you want to set up your equations. But we actually get this wave type motion, or thinking of a bobbing buoy as a wave passes by, we actually get things that move up and down. What's interesting about this is we have lots of evidence in nature that we can interpret by looking at circular motion. Think of a pendulum going back and forth. When a pendulum swings back and forth, it can be represented as going around a unit circle. A swing going back and forth can be represented as a unit circle. Think about your air valve on a tire. As it travels around the circle, you're going to see that motion a lot. So we actually see circular motion in a variety of different ways. And one of the fun videos that I have out there for circular motion deals with amusement parks. Because we think about an amusement park, so let's look at an amusement park. I've got my Ferris wheel, right? I got the Ferris wheel, it's moving in a circle. I've got the spindle top thing that moves like this, and we have our people against the wall of the spindle top, right? We've got that one. If I look at my roller coaster, I've got a circle here. I've got a circle here. I've got a circle there. I have lots of circular motion that we utilize tremendously as we go through and have that aspect of it. So this idea that we have translational motion, even though we think and feel and work in that particular dynamic, we actually do an awful lot of circular motion, and we use it to our advantage. So if I have my little Voyager spacecraft coming around the planet, we actually slingshot by using circular motion in order to get our little orbiter to move on to the next planet or the next moon or the next target. We actually can use that to our advantage. So we have a lot of different things in circular motion. So let's start defining some of the terms that we're going to have to deal with. This is where you have to be very, very cognizant of what your calculator is in. All right? Because if I go in here in my calculator, now this one, I'm going to scroll in here. I'm in degrees, and we've been using degrees all semester long. We're about to change that. I have other modes of my calculator, and on this calculator I have a degree button, and I can change it from degrees to radians to gradians. We are going to be working a lot in this chapter in radians. We're going to be working a lot in radians, so when you're working your homework, the first thing you want to make sure is if I'm working in degrees and I'm doing the calculations, things may not work and you may not get the actual numeric answer. So you're going to have to be very cognizant that you're in gradient or radians. So now you can actually tell which way you're in your calculator. So other calculators are going to do something very, very similar, but you want to be in radians. Radians are special. Now remember way back at the beginning of the semester, we talked about how numbers have units. And my units, like 3, if I had a number 3, I needed to tell you whether it was feet, meters per second, acceleration. The one number that we had out there that we didn't talk about that has no units is pi. Pi is actually a ratio, okay? It's actually a ratio, and it comes from our lovely unit circle, which is why we have it. So if I have a circle, and this is also some interesting things that we have to worry about in our circles. Typically, we start with this being 0, okay? And we travel counterclockwise. Even though our clocks go the other direction, when we're dealing with our coordinates and our coordinate systems, we go counterclockwise, and we come over here, and this is pi. So if I'm dividing up my circle, and I'm going back to my good old mathematics class, this is pi over 2, this is 3 pi over 2, and this is also 2 pi. 2 pi is the circumference, or 2 pi is the degrees that I'm going to travel in radians. So this is, when I have 2 pi, this is in radians. Now, if I am walking this circle, like I'm walking a maze, if I'm walking around here, the linear distance that I travel, and I can take a tape measure and actually do it, is going to be the circumference of my circle, which is 2 pi r. And if you want to review some of this, this is in Appendix 4 and Appendix 5. We've got information related in Appendix 4 and Appendix 5. And our angle that we've got, we're going to be measuring in radians. So our angle is going to be measuring in radians. So we can convert between radians and degrees fairly easily. Pi radians is 180 degrees. 2 pi radians is 360 degrees. And pi over 2 radians is 90 degrees. So we get it. Now counterclockwise, even though we don't like that, that's contradictions the way that things work, that's going to be a positive direction. And that comes into play when we're gonna deal with torque and we deal with other motions, that counterclockwise is gonna give us the right direction. So you're gonna have to look at a thing called the right hand rule. So make sure it's your right hand. Common mistake is because most of us are right-handed, we put our pen in our right hand, and when we're working our problems, we do over here with our left hand and do things with our left hand, and you're gonna be backwards. This is a right hand rule. Mother Nature is chiral, okay? Mother Nature is chiral, and chiral means that if I have my two hands, they are opposite. I cannot put a left-handed glove on my right hand. I'm chiral. I have a left and a right hand. They're mirror images of each other because I can go back and forth across them, but Mother Nature is very chiral. And our bodies and a lot of our physiological processes are very chiral. That's why sucralose, which is a left-handed sugar, the body can't use, and so it essentially has 0 calories for us, versus glucose, which is the one the body uses. We can use it. It's because the things are in the right spots. But I have left and right hands, so I've got to make sure that I'm following that. When we do mathematics, we do something that's the right-hand rule, and if I put my fingers along the direction of motion and my thumb comes up here, what we're going to see is, in the case of electricity and magnetism, my charged particle is going to move in the direction of my thumb because that's the direction of the force. When I'm using a screwdriver, righty-tighty, right? If I'm turning it this way with my right hand, I'm going into the page with the screw. Or if I'm turning it this way, my screw is coming out of the page when I have my right hand rule. So there's a lot of things that we're going to use with right hand rule that's going to give us our direction. And so if I have motion along this circle, I'm going to get a direction that's coming out of the paper if my fingers are traveling around. If I'm going the other way, I'm going to be traveling into the paper. And so what we're getting ready is chapter 7 is starting to talk about rotational motion in terms of just the kinematics. Chapter 8 starts talking about torque. And most of you had the balancing act in the lab this last week, where you were balancing with the meter stick. And you're balancing the forces, and torque is a little different because it's a force acting at a distance or through a distance. Okay? So we have a lot of things with that right-hand rule. So counterclockwise is positive. Counterclockwise is positive. So if I'm looking at how I'm traveling around my circle, my angle can be represented as S divided by the R, where this is my arc divided by the radius. So that would be my linear motion that I'm traveling. So I can represent this. Here's my R, this is my S, and that's my angle. So the angle that I'm moving through is going to be directly related to my distance. So I can go back and forth, because if I do an R theta, I can measure how far I travel around the arc. So we're going to get the same things that we got before. We're going to get a change in displacement. We're going to get a change in angle with respect to time. We're going to get a change in our velocity with respect to time. We're going to get the same kinds of things. So if I look at this, so I'm going to start here, and I'm going to move through an initial angle. So this is going to be my initial angle. And then at a later point, I'm going to be up here. This is my final angle. My change in displacement is just going to be my final angle minus my initial angle. just like I had in terms of my translational motion, except this time I'm traveling around in an arc. And we can look at it in terms of our change in displacement, which was x final minus x initial. So we can do the same things that we did before. Velocity was the change in x with respect to the change in time. So it was my x final minus my x initial divided by my time final minus my time initial. I can do what we're going to call omega. This is going to be my change in angle with respect to time. So I'm going to get my angle final minus my angle initial divided by time final minus time initial. And this is referred to as it has direction. Okay? It has direction, but it's also, we can talk about an angular speed. And if I use my right-hand rule, the direction is out of the paper.
Omega equals.
Yeah, with my angular speed, this is a little omega. Now, a lot of you have seen omega before, because let's look at the units. Right now, if I talk about this, I have radians per second. Okay? Typically, the thing about radians is because radians is a ratio, radians we don't necessarily write out that unit. And radians will actually go away, and this is 1/seconds. So think about that we've seen 1/seconds before. If you've been in chemistry class, you've seen 1/seconds a lot. It's hertz. Okay, it's hertz. So 1/seconds, so if I'm looking at, that's why I talked about that projection moving back and forth, because if I have a pendulum that's going back and forth, we have a period, right? The period is the time that it takes to make a complete cycle. So the period is the time to make a complete cycle. There we go. And frequency is equal to 1 over the period. So frequency is 1/seconds, and we've defined that as hertz. And frequency, we've seen a lot depending upon what you're working in. If I'm in chemistry class, frequency is written with that symbol. It's a little v, it's a scripty v. Or it can be written with an omega. So you'll see frequency as an f, this scripty v, or an omega, depending upon how I'm using it, and depending upon where I'm at. But it's 1/seconds. And if you think about that, what's happening in our unit circle, and we started talking about that when I first went, the time that it takes to go all the way around is the period, and the inverse of the period is the frequency, and I've got wave motion here that I can look at. So we see this over and over again, and we're going to start seeing how these things relate. So understanding our rotational motion it's kind of important. Now, remember what we did back when, right? What we did back when was I started out with a change in velocity. I started out with a change in position with respect to time, and that was this. And we also did a limit as the change in time got very, very small, and that gave us an instantaneous velocity. We got an instantaneous velocity. Well, guess what? I can do the same thing now. and I can get an instantaneous. So my average omega is just going to be my change in angle with respect to time. And I can have an instantaneous which is going to be that limit as time approaches 0 of that change in angle with respect to time. And that's going to be my instantaneous one. So we can do a couple of things. Let's just do a quick problem. I've got a wheel, moves uniformly from rest, or no, we're just going to do, we got uniformly from an initial angle of pi over 2 to a final angle of 3 pi over 2 in 20 seconds. So my change in angle is just going to be my 3 pi over 2 minus pi over 2, which is going to give me, so I got 3 halves minus a half, I get pi, right? So it moved 180 degrees, if I want to think about how that moves. But it did it in 20 seconds. I'm going to get my change in angle over my change in time, which is going to be my pi divided by 20 seconds. This is going to give me 0.16 radians per second, or just 1 over seconds. If I wanted to know the linear distance traveled, I have to have some additional information. We need the radius. So let's say the radius equals 2 meters. So if my radius equals 2 meters, I traveled r, so I'm going to have the distance is just going to be r theta, which is going to be 2 times pi, which would be 6.28 meters that we traveled.
Distance is r
R times theta.
theta
Mhm.
and 2 pi.
Yeah, so, and if I convert pi, it gives me my 6.28. So think about this for a second. This gives us some implications, right? Everybody's ridden a merry-go-round, right? Everybody's been on a merry-go-round, carousel, merry-go-round. So let's look at this for a second. If I'm on a carousel with carousel horses, all right? Or if I'm doing a quadrille where I've got a person in the middle and I got a person out here, okay? Or I'm turning a variety of things. Think about what's happening here. The person that's on this spot going around is going to experience the same change in angle as the person out here way out at the edge, or the person here in the middle. Going around the circle, I'm always going to experience the same change in angle. That angle is still theta. This angle is still the next theta 1. This angle is the next theta 2. They're all going around the circle at the same rate of changing angle. But the linear distance that they travel is significantly different. Okay? The linear distance that they travel is significantly different. The person out here is going through a greater linear distance than the person in here and the person in there. They're all traveling with the same angular speed, but my linear distance is significantly different. Again, this is what makes amusement rides more fun. Because the mechanics to going around that circle or to getting the turntable to go around, it's going to be the same. So let's talk about that turntable going around. If I have a good old vinyl record, remember vinyl records, there are typically 3 speeds, right? 33 1/3 RPM, 45 RPM, and 70 RPM. I don't know what the one is in your CD player, okay, but your CD player's doing the same thing too. Now think about what that means. That means revolutions per minute. So if I'm converting, and you're going to get homework problems that talk about this, and you're going to go, wait a second, they haven't given me the speed. Yeah, they did. They gave it to you in revolutions per minute, which means 1 revolution is 2 pi in terms of angle. So if I'm doing 33 1/3 revolutions per minute, I'm doing 33.332 pi angles per minute, which is 60 seconds. So you have to think through the information that it gives you when you're looking at revolution. My car tire rotates at 20 revolutions per minute or 20 revolutions per second. They actually gave you a speed, you just have to convert that information into a speed. So if I actually do the 33 1/3, that's moving with an angular speed of 3.49 radians per second, or 1/seconds. So think about, when you're thinking about rotational motion, we actually do a few different things, and it has some different implications. Okay, so what is the next thing we did after we did velocity, right? We did velocity. So if I did velocity is the change in position with respect to time, we did acceleration, which is the change in velocity with respect to time. So if I'm doing, my omega is the change in angle with respect to time, I'm going to get an angular acceleration. We're going to use a script alpha. That's going to be my change in my angular velocity with respect to time. We can do the same kind of a limit, okay, to get our instantaneous. So now if I have a wheel, I'm going to start with an angular velocity of 0 or at rest. I'm going to move up so that I get 5 radians per second after 30 seconds. We want to know what my angular acceleration is. Well, that's just going to be my final minus my initial divided by my change in time. I started at 0, so I get 5 radians per second minus 0 radians per second divided by my 30 seconds gives me 0.17 radians per second squared, or I can just write this as 0.17 inverse seconds squared.
That's squared?
Yep, because it's an acceleration.
angular?
Angular acceleration.
So you just write A or you write WA?
There's no WA.
Okay, just A?
It's an alpha.
Alpha? Oh, okay,
It's an alpha.
sorry.
Okay, rather than bore everyone with the same derivations that we've done before, because everything so far has worked exactly the same way, we get, if I look at V final is equal to V initial plus AT, I get my change in X is equal to V initial times time plus 1/2 AT squared, and I get V final squared is equal to V initial squared plus 2A change in X. I'm going to get omega final is equal to omega initial plus alpha T. I'm going to get my change in angle is going to equal omega initial times time plus 1/2 alpha T squared. And I'm going to get omega final squared is equal to omega initial squared plus 2 alpha change in angle. I get parallels in my equations for rotational motion as well as my linear motion. So guess what the problems are going to look like? They're going to look very similar to what you've done before. They're going to look incredibly similar to the things you've done before. And speaking of which, I think there's a quiz on momentum in Blackboard. Okay, I think I posted a quiz, and I think I have it due Friday-ish. Friday at 8 a.m.? Was it Friday or Saturday?
It's Friday.
Yeah, I thought I changed the time so it wasn't right at 8 a.m., but I'll double check. But there is a quiz on momentum out there. All right, so we're gonna look at our wheel again, because the wheel's an easy one to start with. We're gonna have a constant angular acceleration of 3 radians per second squared. And we're going to start with an angular velocity of 1.5 radians per second at time t is equal to 0. We want to find the change in angle from t equals 0 to t equals 1.5 seconds. We want to find the angular velocity at t equal 3 seconds. Alrighty, so if I want to find the change in angle from t is equal to 0 to t is equal to 1.5 seconds, I'm going to do change in angle is equal to the initial time times time plus 1/2 alpha t squared. This was 1.5 radians per second times, we're going at 1.5 seconds, plus 1/2 3 radians per second squared times my time, 1.5 seconds squared. Seconds cancel, so I'm in radians. Seconds squared cancels, so I'm in radians, so I can actually add these two things together. I get 2.25 radians plus 3.38 radians, which gives me 5.63 radians. But if you're like me, you go, well, I don't know what that really means, because I don't think in radians. So I may want to convert it to number of revolutions. Well, if I take 5.63 radians divided by 2 pi revolutions per radian, well, that's radians per revolution, radians per revolution, that gives me 0.90 revolutions. So it didn't quite go all the way around at that particular angular velocity, or that a particular angular acceleration. Didn't quite go all the way around. So now I want to calculate the angular velocity at 3 seconds. Well, angular final is equal to angular initial plus alpha t. I started out at 1.5 radians per second. I'm doing a 3 radians per second squared acceleration, and I'm at 3 seconds. That cancels that, so I'm in both of these units are radians per second, so I can add them up. I get 1.5 radians per second plus 9 radians per second gives me 10.5 radians per second. So these problems look very, very similar to the types of problems that we had before. And we can go back and forth between our linear motion and our angular motion, because we can relate our angular quantities back to our linear quantities, just like what we've seen all along. If I'm in my coordinate system here, this is my y and this is my x, r is going to equal the square root of x squared plus y squared. My angle goes back to the arctangent of y over x, just like we've been doing all along with those vector quantities. That looks a little better. It's been fuzzy, hasn't it? I can't tell if it's me or the screen. So we can go back, if I'm looking at my vectors, or looking at my angular motion as I'm going through curves. This is going to be my velocity at any given point along the curve. Because we know this, right? Because if I'm slinging a slingshot and the string breaks, it's going to go off in a straight direction. It's going to go off in a straight direction. So my angle is going to be S over R. So I can go back, and that R times my angle is going to be S. So if I do a change in angle with respect to a change in time, I'm going to do this as 1 over R, change in S with respect to time. This is going to be omega is equal to V over R. I'm going to get R omega is equal to V. And if I do that, if I get my change in omega with respect to time, that's going to be 1 over R, change in velocity with respect to time, which is going to give me my alpha is equal to omega over R, and my omega is going to be R alpha. Oops, did that wrong. That's not omega, that's V. We'll try this again. That is A. That is alpha. Thank you very much. R alpha is equal to A. And I knew that wasn't right because we get something else. Because we will actually get centripetal acceleration. The center-seeking acceleration will be, this is an alpha, so this looks better.
And that's alpha?
It's an alpha, so it's R alpha A. Okay, so what this gives us, folks, is that we end up with an acceleration as we go around the circle. So as I'm going around the circle, and I encourage you all to look at the videos because they're better than my drawings. We get, this is a velocity, even if I am traveling at a constant linear speed. So I'm hitting this at 60 miles per hour, and I'm going around the circle at 60 miles per hour, I have a constantly changing acceleration because I have a change in direction. And we've already seen this, and I end up with that change in direction, and one of the videos does a really nice way of showing the vectors and bringing these vectors in here. I get a center-seeking acceleration in each one of these, and this center-seeking acceleration is called my centripetal acceleration, and that's v squared over r. Centripetal acceleration is a v squared over r. I also have a little tangential acceleration that I get, and the combination of that is the actual acceleration that I experience. And if I'm looking at the magnitude of that actual acceleration, it's going to be my centripetal acceleration squared plus my tangential acceleration squared to give me the overall acceleration that my particle or my person or my car is going to experience. So we have two different types of acceleration that we have to consider when we're traveling around the circle. That's why things get complicated. But the centripetal acceleration piece gives me my artificial gravity if I'm spinning in a satellite, or it allows me to run the human loop that we saw before, or it allows a car to hit the loop-to-loop, because I'm going to be able to balance that out and be able to work with it. So that we've got that aspect as well. And I definitely encourage you to watch the videos because the videos really, really help explain it. So what we're going to do is we're going to work a problem here. We have a disc. The diameter is 30 centimeters. It is rotating with a constant angular acceleration of 2.25 radians per second squared. We're going to start at rest. And we're going to draw a line from the center to a point P on the rim. Which is located at 50 degrees from the positive x-axis. At t equals 2 seconds, find the angular speed, the linear velocity, the tangential acceleration, of P, and the position of P. Okay. This is not an uncommon problem. So the first thing you've got to do is figure out what the problem is telling you. So we've got a disk, so I'm drawing a disk. Got my disk. All right, we've got a point P on the rim somewhere, but it's telling me my point P is located at 50 degrees from the positive x-axis, so I'm going to give myself a reference point. It's telling me my point P, I've got a line drawn here, there's my P because that's 50 degrees. Okay, so that's the first thing. I got to know where my point P is. We're told that I've got an angular acceleration of 2.25 radians per second squared. My R is 30 centimeters. I probably don't want it as 30 centimeters. I probably want it as 3 meters, so I'm going to go ahead and convert it over. We know my initial angular, or my angular velocity is 0 because we're starting at rest. And we want information at t is equal to 2 seconds, and what information we want is the angular speed, the linear velocity, we want the tangential acceleration, and we want the change in angle of P. So the trick to these problems is figuring out what's my starting condition and what information I have and what information I need. And at that point, it doesn't necessarily, you don't necessarily have to work it in order, okay? So I'm going to do my angle final is equal to my angle initial plus alpha t. And we know that that's 0 plus 2.25 radians per second squared times my 2 seconds. And that's going to give me 4.5 radians per second. Well, V is equal to R omega, so that's just going to be my 0.3 meters times my 4.5, and that's in radians per second. And this is what happens to us when we do this. This is why we drop the radians, because I'm going to end up with 0.675 meters per second. Now my tangential acceleration is just R alpha. So that's gonna be my 0.3 times my acceleration that I've been given. And that's gonna give me 0.34 meters per second squared. If I wanted my centripetal acceleration, that's v squared over r. That's going to be my 0.675 meters per second squared divided by 0.3 meters. And that gives me 1.52 meters per second squared. So my total acceleration is going to be my 3/4 squared plus 1.52 squared. Gives me 1.56 meters per second squared. That's the total acceleration. We also want to find our change in angle. Change in angle is equal to omega initial times time plus 1/2 alpha t squared. That was 0. So it's going to be 1/2 2.25 radians per second squared. 2 seconds squared gives me 4.5 radians. But I want that, but that's my angle final minus my angle initial, and now I have to get, my angle final is gonna equal my 4.5 radians plus my initial angle, and we said that was 50 degrees, so I have to convert it. So pi over 180 degrees gives me 4.5 radians plus 0.873 radians for a total of 5.4 radians. Converting it to angle so that we know what that is, that's going to be 309 degrees. And that would be 180 degrees divided by pi, which gives you that conversion back there. And so what happens here if P was at 50 degrees, I end up down here where this angle is 309 degrees. Okay, I think I'm going to stop there. Guys, good? Alright, I didn't hand you your test when you came in, because I had some of you come in late. I've got your tests. They're over here. No. Okay.